is true. If x and y are both negative, then xy is positive. This also, like the previous case, I leave to you to figure out. And we have, so since xy is positive, this is equal to xy, but that can be written as minus x times minus y. Now from negativity of both x and y, these quantities are equal to the absolute values. If x is positive and y is negative, then xy is negative. In this case, xy is negative. And we have, now because xy is negative, this is equal to minus of xy, which can be written as x times minus y. X is positive, so this is equal to absolute value of x. Y is negative, so we have this. And you can clearly see that the only other remaining case where x is negative and y is positive also can be handled similarly. So that we just mentioned like this. The case where x is negative and y is positive can be similarly handled. Okay, so this proves our identity. Now, just like the previous part, this part also has a special case. From this, I think I need ink. From this, we have, now we have also been asked, besides this identity, to prove that the absolute values of a rational number and its negative are the same. So that can be obtained by taking y equal to minus 1. Absolute value of minus x equals x times minus 1. So from our identity we get this, which is equal to x. So you just apply the definition here. This absolute value will be minus of minus 1, which is 1. So we are left with absolute value of x. So this completes part D. So after part D, we now have part E, which we now have things about distance. For absolute values, we have proved all the things. In part E, we are asked to prove that distance between x and y is always greater than or equal to 0, and it is equal to 0 if and only if x is equal to y. You just have to notice that this by definition is nothing but an absolute value. That means we have to prove this, and this is equal to 0 if and only if x is equal to y. From non-degeneracy of absolute value, we directly have this inequality, because all absolute values are non-negative. So in particular, this one is also non-negative. From that same non-degeneracy of absolute value, we know that this is equal to 0 if and only if x minus y is equal to 0, which is equivalent to x being equal to y. So from part A, this result follows directly. So without writing anything much, we just simply write like this. This part follows from part A. In part F, we have been asked to prove that distance is symmetric in this sense. In other words, we have to prove this, or this. And we have already seen that that follows from here. Absolute value of a rational number and its negative are the same. So this one follows from part D. It follows from part D. And finally, in part G, we have triangle inequality for distance. So that will follow from the triangle inequality for absolute value in this way. Here we will write something from part B. We have d of x comma z equal to this, which can be written as plus y minus z. Now we use part B, that is triangle inequality for absolute value. It's equal to this plus y minus z, which are nothing but this and this respectively. So that is the triangle inequality for distance. This completes the proof of part G, and hence the proof of proposition 433, and hence the solution to this exercise. Okay, now next exercise, give me a moment. Okay, so in the next one, exercise 432. Okay, where is that thing? Did I lose it here somewhere? 432. Now here it is. Prove the remaining planes of proposition 437. Okay, so we start by recalling the parts of proposition 437. Proposition 437 involves properties of epsilon closeness. Okay, so, and if you remember, we have in fact proved one part, namely the last one, and we said that the others will be proved in the exercises. So the first part is this, part A. Here we have to prove that if x, here also we start with three rational numbers x, y and z. If x is equal to y, then x is epsilon close to y for every positive rational epsilon, and conversely. That's what we have to prove here. So let's do the easier implication first. First, assume x is equal to y. Then for every rational epsilon greater than 0, we have d of x comma y from non-degeneracy of distance, this is equal to 0 and that is less than epsilon. If you want, you can write from proposition 433 part E. So x is epsilon close to y for every rational epsilon greater than 0. Now we prove the converse. The converse is not this easy, but I mean it's relatively more complicated, but just relatively. Okay, it's not trivial. It's easy, no doubt, but not this trivial. Conversely, assume x is epsilon close to y for every rational epsilon greater than 0. Our aim is to prove that x is equal to y. To the contrary, suppose that x is not equal to y. Suppose x is not equal to y, then by non-degeneracy of distance, then by proposition 433e, d of x comma y is a positive rational number. Because d of x comma y is 0 if and only if x is equal to y. Since x is not equal to y here, so this quantity cannot be 0. But we know that this quantity can either be 0 or positive. It can never be negative. So in this case, this is a positive rational number. Now you impose the condition that we have assumed. We can take any positive rational number in place of epsilon. Thus, x is this close. This is also a positive rational number. I mean, if this d value is positive, divided by 2, that is also positive and rational. So this is x is this close to y. That is, d of x comma y is less than or equal to 1 by 2 times d of x comma y. That is, this one implies 1 is less than or equal to 1 by 2. What we are doing here is that we are dividing this inequality on both sides by the reciprocal of dx comma y, which we can do without changing the direction of the inequality, because this is a positive rational number. So its reciprocal will also be a positive rational number. So here we have used the thing which is named positive multiplication preserves order. Which is not possible. So our supposition is from, that is, we must have x equal to y. Okay, so this is part A. In part B, if epsilon is, if x is epsilon close to y, we have to prove that y is also epsilon close to x. That means we are given this. We have to prove this. Now this it automatically follows from this. This one follows from this because these two things are equal, and that comes from symmetry of distance, or proposition 433 part F. So we have understood how it comes. We will just now mention that, since it's very easy. That's it. That is part B. Then part C. Okay, in part C we are given two positive rational numbers epsilon and delta, and also it's given that x is epsilon close to y and y is delta close to z. We have to prove that x is epsilon plus delta close to z. Given x is epsilon close to y and y is delta close to z. Okay, epsilon and delta are two positive rationals. That thing is understood. Then use triangle inequality for distance. This is less than or equal to dx comma y plus dy comma z. Okay, so this turns out to be less than or equal to epsilon plus delta. Hence, x is epsilon plus delta close to z. So that is part C. Then part D. In part D, what are we given? We are given four things. X and y are epsilon close and z and w are delta close. Then we have to prove that x plus z and y plus w are epsilon plus delta close, and x minus z and y minus w are also epsilon plus delta close. So in this case, we are given this. Then we forgot to mention that we are using proposition 433 part G here, but that is understood. You can clearly see we have used triangle inequality of distance. Then so we continue to use such things without mentioning from where they are coming. Their use is obvious. So then yes, distance between x plus z and y plus w. We apply the definition of distance. This is x plus z minus of y plus w, which can be written like this: x minus y plus z minus w. Use triangle inequality for absolute value. This is equal to d of x comma y, and that thing is equal to d of z comma w. The first term is less than or equal to epsilon, the second one is less than or equal to delta. And we also have one more thing to see. Distance between x minus z and y minus w. So this also by definition is this minus z minus y minus w. It can be written as x minus y plus x minus y plus w minus z less than or equal to this plus w minus z, which is equal to d of x comma y plus d of w comma z. But from symmetry of distance, this is equal to this, which is less than or equal to epsilon plus delta. So that's it, that's what we want. So x plus z is epsilon plus delta close to y plus w, and x minus z is also epsilon plus delta close but to y minus w. So this is part D. Okay, then part E. In part E we are given that x and y are epsilon close. We then have to prove that x and y are epsilon prime close, where epsilon prime is a rational number greater than epsilon, which you can see is it follows directly from the given condition and transitivity of order. So here, I foolishly wrapped that up. I have to again write it now. Given this, so far any rational epsilon prime greater than epsilon transitivity of order implies actually it will be strictly less than epsilon prime, but we can write this one also. This is more general. Thus x is epsilon prime close to y. So that is part E. We have three more parts. Part F. Part F is slightly complicated, but we will see. So in part F we are given, so let us start by writing what we are given. It is given that y and z are both epsilon close to x. That means y is epsilon close to x and z is also epsilon close to x, and w is a rational number lying between y and z. In this manner or this manner. Okay, we have to prove that w is also epsilon close to x. Let us assume that the first set of inequalities hold. Okay, now not D. We have to start by considering the minimum of the distance between, I forgot the step. We have to consider the minimum of the distance between y and x and z. Okay, minimum of minus y minus x and minus absolute value of z minus x. Why suddenly we are taking this, we will see afterwards. note that the minimum is less than or equal to this either this is the minimum or this is the minimum. In any case, the minimum is always, since it's by definition the smaller one, it will be less than or equal to each one of them. We are considering this one, okay, and this is less than or equal to y minus x. Where is this inequality coming from? It's coming from this. Proposition 433 part C. There we proved this. So we are using this part of the inequalities here. Okay. Now you look at the inequalities we have assumed here. Subtracting x from all the terms, we get y minus x less than or equal to w minus x less than or equal to z minus x. And z minus x is itself less than or equal to its absolute value. Again we are using part C of proposition 433, and this in turn is less than or equal to the maximum value, maximum of these two things. Okay, because by definition the maximum, just like this one, the maximum is greater than or equal to both the things. If, okay, now either this is less than or equal to this or strictly greater than this. So two cases are arising. If this is less than or equal to z minus x, then the above inequalities give us, okay, if this is less than or equal to this, then minus of this will be greater than or equal to minus of this. Inequality gets reversed when we multiply by minus 1. So minus of this is the greater one. So the minimum will be minus of this. That means in this place we will have minus of this. That is less than or equal to, we ignore the intermediate terms and we concentrate only on this one, w minus x, which is less than or equal to, this one is the maximum, I mean the bigger one, either they are equal or and this is greater. In any case, this will be the maximum. So by proposition 433 part C, we have what do we have? Distance between y and x, which is nothing but this absolute value, is less than or equal to this, which is nothing but this d value, and this d value is given to be less than or equal to epsilon. Do you realize what we have done here? Minus y is less than or equal to x is less than or equal to y, that implies absolute value of x is less than or equal to y. That's the thing we have, in that way we have used this part C of the previous proposition. Similarly, if, but all of what we have done depends on this if, right? If this inequality is true. On the other hand, if this is greater than z minus x, then instead of performing the calculation, you just look at what will happen here. In place of absolute minus of this, we will have the other thing, right? Minus of mod y minus x, that will still be less than or equal to w minus x, which will be less than or equal to this thing. Now because here this one is the greater one, we will have mod y minus x. So in this case, will be less than or equal to y minus x, which is equal to this. So again this is less than or equal to